Okay, we're live.
This is the Go Meetup, Go Miami. It's October 15th. Thanks to everyone coming out. We're hosted at Ultimate Software this time here in Weston. We have a speaker today, Ryan Leavengood, who's going to be talking about TLS and SSL and Go. So without further ado, here's Ryan.
Thanks. So yeah, my name's Ryan Leavengood. I'm a senior engineer, software development at Dell SecureWorks. I get to work from home, which is nice. And Dell SecureWorks is based out of Atlanta, and it was an independent security company that Dell bought about 5 years ago. So we do a lot of the security for like some big companies that you probably have heard of, but I can't say what they are. So I want to talk about TLS and SSL. You probably know what those stand for, but I'll talk about it a little bit. First, I wanted to ask though, does anyone here know like a good amount about TLS? Okay, a little bit. It's a lot of text here, but basically, the whole idea of having secure sockets came out from Netscape, and it was originally called Secure Sockets Layer. And as you might expect, there was various flaws discovered in that, and they kind of had to do something very similar but different enough that they renamed it and called it transport layer security, and I apparently misplaced the words there. But TLS, it's transport layer security, and it was implemented and released in January '99. And there was an update. I think 1.1 was in 2006, and 1.2 was released in 2008. They're working on 1.3 now, which is interesting. 1.3 is going to be all ephemeral, which I'll explain what that means. Key exchanges. So 1.3 is all about forward secrecy, and I'll explain what that is too later. So yeah, the idea, once 1.3 is out, fully deployed to all the browsers, you don't have to worry about the NSA quite as much, at least. And I want to talk about the NSA too, and like their supposed godlike powers. Actually, I'll have it real quick. So the whole thing, they spent years. They planted guys in some of the security committees. Spent years. They came up with this ridiculous random number generator algorithm that was so complicated nobody could implement it right, and it was designed specifically because they knew the one little secret number to be able to predict it. So what happens when you can predict a random number generator or cryptography? You can break cryptography. So that was their evil plan to get into, be able to do man in the middle and decode your SSL and your encryption. They came up with this crazy, and like it took a couple security engineers about 5 minutes to look at that and say, this is ridiculous, and they figured out that it was broken. And so that pretty much has been turned off in like all browsers. And so that was the NSA's, and so those TV shows you watch, like one of my favorites is Arrow, the Green Arrow TV show on CW, and the little hacker girl in the show, it's like, okay, this is encrypted. No, it's not. That is not how it works. The whole idea behind almost all encryption is crazy, crazy, crazy math that says that it is impossible for you to undo this thing. Like if you take two really big numbers and multiply them, and you get another number, tell me which two numbers were used to multiply to get that number. It's impossible, and no matter how many resources you put into it, it takes literally like 1 trillion years to brute force it. So if you want to learn a lot more about TLS, the Wikipedia entry is really, really, really good. It's got like all these tables of all the different protocols and who supports what, and the version and how crappy IE is, pretty much. But lots of cool stuff. All the you can learn, like in a paragraphs, all the different security like problems that came up. They've had various fixes around, so that's very, very much worth reading. So this is very important. To set up a TLS connection, you do what's called a handshake. So I've done this kind of ASCII, very laid back version of it. So basically, whenever you have any kind of TLS connection, whether it's HTTPS or anything, this is pretty much what happens. As I say on the bottom, the details vary a little bit, but this is basically if the client says, hey, I support this version of TLS and these different cipher suites, and I'll talk about what cipher suites are after this slide. And then server says, okay, how about we use this version, these number of suites? And one little thing about that is Amazon like uses something really kind of crappy because it uses less resources. So AWS. And then they give you your certificate, or the server says, you know, hey, okay, well, let's use this stuff, and here's my certificate. And the client does some validation of that. So it's like, is the certificate, there's a chain. So the certificate that your server delivers has a chain of, like, usually there's an intermediate certificate that your certificate authority has, and the actual root certificate authority, and it checks that that is a valid certificate authority. And so we have this whole system where, you know, several hundred companies all over the world have done the things necessary to get like certified as a CA. And one thing they have to do, actually, their root certificates are on a machine that's not on the network in what's something called an HSM, hardware security module, that if you try to like tamper with it, it blows itself up basically. And so they're actually pretty secure, and that's why they have intermediate certificates that they actually sign your certificates with, because they literally have to like have somebody go with a, you know, totally clean USB key to like get an intermediate certificate to then sign yours. So anyways, the client checks their certificate, looks at the CA, does the domain names embedded in the certificate match the host I'm at, things like that. So when you see those little errors in Chrome or whatever about this doesn't check out, doesn't look right, that's what's happening. The browser's checking those things for you. And Go does all these checks too when you connect to something. So at that point, if the certificate checks out, what happens is here is in the hello message, each side is sent a random number. And then the client takes those random numbers, the one it generated, the one it got from the server, it adds another bit of entropy, another random data, and it basically encrypts that with the public key that is embedded in the certificate. So only the server can decrypt that. So that goes back to the server, and actually both sides kind of use those shared secrets to generate a key. But yeah, actually, see the details, even though I'm like, eh. But basically, the whole point is because public key cryptography is kind of inefficient, you know, having the public-private sides, all the actual communication is encrypted with symmetric encryption, which basically means each side has the same key. So that's the problem SSL is solving, or TLS is solving. How do you take and get both sides to have this, you know, temporary key that we're going to throw away when it's done and share it over the public internet without someone else stealing what it is? So that's how all this stuff is. That's what it's all about. So at this point, they should have the same key. And so the client says, okay, let's start doing encrypted communication, and I'm done. And the server verifies these are actually encrypted with this. So it verifies that those check out, and then it does the same thing. And the client verifies. So a lot of checks are going on here, but it's all pretty quick on modern computers. So once that's done, if there haven't been any errors, you're good. And you've done the handshake, and then you can actually talk HTTP or whatever other protocol. It's not just HTTP that's basically, you know, that can be encrypted. So this is the big list of cipher suites, and I actually only just learned what some of these mean. This looks like a bunch of like, oh my god, what does this mean? So they're all prefixed with TLS because that's how we do constants in Go. But the first part is the key exchange for the public-private key. And all these E's, that's all the ephemeral, Diffman, or Diff Huffman.
Like Diffie
Hellman. I didn't know their names, poor guys. But that's all the ephemeral stuff, and there's different kinds of DSA, RSAs and this is the actual encryption used after the handshake. And then the GSM and the CVCs and the SHA is the message integrity checks. So basically, this is how we exchange keys, this is how we communicate when it's encrypted, and this is how we check the messages came through properly. That's what all these different combinations are. And there's more than this, but this is what is supported in Go. But I thought it was kind of neat to see like how they're broken down. So forward secrecy, like all those ephemeral key exchanges, basically it keeps it where anything that's not ephemeral, if the NSA, which is probably the main person doing this, or anybody saves all your encrypted communications, if they later can compromise the server, if it was not an ephemeral key exchange, they can actually decrypt all that past stuff. So that sucks. Because at some point they'll be able to get into the server knowing them. So with this, basically a random public key is generated in an unpredictable way per session. And even if they figure out what that key is, they'll only be able to decrypt that one set of messages, that one session. That's another point during the exchange. You don't redo this every time you connect to the same server. Usually you'll say, hey, here's a session ID that you gave me before, and the server can usually just resume that. The server keeps track of some of this information, so you can just resume the same session. I don't know if there's some kind of timeout. I'm not really sure the details of that, but there's a way to at least, like, in one little session of, like, when you first connect to Gmail or wherever, it'll use a lot of the same stuff, so it's not having to redo that handshake every time. So if you want to set up your own, certificate, it's kind of hard. I mean, I've commented this open SSL command, and I mean, if you read it, it's not that bad. We're doing a request, and I don't even know exactly what it's like, an X509 format. I want a new key with this private thing and this file and this certificate. I mean, and then nodes, or if it's node DES, is no password. I have no idea if that's nodes or if it's node DES or what. And that's how many days. So I mean, who can remember that without having to search? I can. If you actually want to try to, like, program against OpenSSL, I had a problem. I was trying to figure out how to generate this hash that is in Linux. Basically, it's pretty smart. They hash all the root certs that are in the etc directory, and so when they get a certificate, you can quickly find which one it is instead of having to scan them all. So it's pretty slick. They like do some, and I was trying to figure out what the algorithm was, and I started looking at the OpenSSL code, and then I died. Once I was alive again in the hospital, I said that was enough of that. So all right, I'm being a little silly, but it was I couldn't figure it out actually because, like, the way the code is, it's you have to know a lot of the code base. You can't just look at one little piece and figure it out. Whereas, in my opinion, in Go, you can kind of read the code of the core library and pretty much figure it out. So this is how you do that in Go. This is all the code, and you're like, oh my God, it's a lot of code. But this is all doing this in Go code that you can understand. You can change that this, like, is doing, and there's all kinds of crazy stuff behind that command. So basically, to make it fit on the slide, I've gotten rid of all error handling. So should be an error handle there, and then in this function, which I'll show you next. But basically, that's how you generate a key. Pretty easy. Ran.reader is cool. That actually reads from the cryptographically secure random number generator that's on almost any machine. And that probably on Linux connects to dev random or dev random. That's the number of bits of the key. It's kind of the same as this parameter. And so that's your private key. Boom, done. If this is 4096, this can take up to 30 seconds. It actually does a lot of stuff. It's pretty slow. You get the time for this. And this is basically, you build this template, as it's called, by just making your own X509 certificate. You give it a big int serial number. I'm being lazy, just putting 1. You can build the subject, which is this crazy PKIX structure, but you can just get away with putting a common name. Not before today, not after adding a year, basically. These are the kinds of usage. So for signatures, for cert signing, because we're making a CA, and for encipherment, server auth, is it a CA? Yes. And then, I don't know why you need that. Maybe you don't, but you say, this looks good to me. And then create certificate, you give it the RAND reader again, this template twice, and basically one of them is the CA, and one of them is like the actual template of the certificate, like where you put the name. And then you give the public and the private key. And then that returns bytes, the DER formatted bytes. And you can actually take those and then get a certificate that you can use in other ways, which I do in my work stuff. But in this case, I just want to save those to a file. And this is what the save the PEM is. I wrote that. File name, again, skipping the error, but that's pretty much all it is. PEM encode does almost all the work. You just give it a IO.reader. And the kind of thing it is, which is really just literally that string, like you see if you ever look at a cert, which I'll show you in a second. So 37 lines of code, pretty cool. To generate a private key, a self-signed cert, and save in PEM. And that's literally this is being pulled from the code or from the directory this is in. That's the cert. So that part is that thing you add here. You know, the temp type. So this is a really stupidly simple Go server. When you do listen to serve TLS, the easy way is to give it these two temp files and simple handler, and apparently it's not working. Probably because Chrome is like, I don't know what this is. It'll probably complain. Oh, is it running? All right. Yeah. Running. Well, that's how you fail at running
Live demos.
Demos.
Live demos, yeah.
Yeah. Oh, maybe actually you need HVS, then I don't, because I'm not listening. Your connection is not private. So this actually segues nicely, because the next part of my slide, which I'm going to go back to, is this concern. Safari actually complains very little. Like you load it once and it's like, okay, that's fine. Because I did a lot of this on Safari. So because that certificate, and I was actually using my CA certificate, which you really shouldn't do, but for this demo it was fine. You can actually use that CA certificate and with very similar Go code generate certificates you can use for your server. This is some of the stuff that I'm doing for my work project. I work on this cloud security project, kind of doing stuff with Docker. So that's why I've learned some of this. I didn't know anything about SSL before like 6 months ago. So there's a way around this. Like this is kind of what you do on Linux. So if you're doing something in Docker or you're developing in a Linux server and you want to add your own CA, you put it in this user share directory and you run this command, which is on pretty much all the distros. And this basically does a bunch of the magic to copy that certificate into the etc SSL directory and make that like SHA or that hashed name that OpenSSL looks for. That's the reason there's a whole command for it, because it's complicated. You can also add these in Windows and OS 10 pretty easily. I don't know the automatic way to do it, but it's possible. So if you want to make your own little private CA and your own little secure service, you could do that, and this is how you would do it. But we have a new hope. There's this project, I know Mozilla is involved and some other companies, called Let's Encrypt. And it hasn't launched yet. They were supposed to launch by now, but later this year. But basically, it is a totally free certificate authority. So if you haven't heard of it, there's their website. It's pretty cool, and they've developed this protocol called ACME, which stands for Automated Certificate Management Environment. And you can automatically set up your CA. Like if you run it on your server, it kind of communicates with their server and does things like, okay, put a file with this random name in this location on your server, and then we'll see if it's there. And so it just shows that you have access to that server that owns that domain. So pretty cool, because I'll tell you, before I knew all about this, I had to get a certificate for one of the websites that I'm involved with, and I didn't know what. I don't know what's going on. It didn't make sense. This should make it a lot easier. So guess what language was their servers written in? It's written in Go. I was going to embed GitHub here, but it didn't like that. I think GitHub says, I'm in an iframe. I refuse to render, because this is what this had iframes. But anyways, that's where it is. Let's Encrypt Boulder is the name of their server, and they have a whole spec, so anybody can actually write an ACME-based CA. But they wrote it in Go because TLS is really easy in Go. Like when you use Go to do TLS, OpenSSL has no say in that, not there at all. The only thing you need is Go understands the layout of the certificates that is in that etc directory I mentioned that OpenSSL supports, and they'll read the root certificates. But otherwise, Go does it all itself. So, which is kind of cool. It means it's probably a lot easier to understand if you want to get into it. And I showed you some of the code that you can write. So when you know these things and you understand how to write this stuff, you can do cool stuff like make something called like Let's Encrypt. You can do your own man-in-the-middle stuff, though there's probably lots of tools for that already. And you can create secure communication that just uses your own CA and do things with that. And you can also create certificates on demand, and actually we've done some of that in the project I'm working on, which is pretty cool. Like you have a CA and someone connects to something that should be secure, but we'll just generate a certificate. So pretty interesting, like once you have that power. So there are 2 certificate structs in Go. This is the one in the TLS package, and it's quite a bit simpler, still kind of complicated, but there's bytes, and this is actually, it's an array of arrays, so it's actually a chain. This is the chain. So when you actually do a TLS request, you'll get some TLS info back, and you can get the certificate chain out of it, and you can iterate over this and take a look at the certificates. There's a private key, there's all this other stuff, and then the leaf is parsed on demand, and that's actually an X509 certificate, and that's the one that's a real beast. It's so big, I just need to put the whole thing. But it's got, basically this represents the certificate you would see defined in the RFC for TLS with all the crazy stuff it has, like the subject. There's actually a bunch of stuff down here, like the parsed subject, and other things. But generally, you don't need to know too much about this. Like if you create a certificate, I mean, most of the work will be done by the Go libraries. But this is actually interesting. I'll talk about that in a little bit. But that's called the SPKI. You'll hear that SPKI used a lot in certificate stuff. And that's one thing it's used for certificate pinning, which might be my next slide. Oh, it is. Wow, what a segue. So this is kind of neat. It's a little bit complicated, as I've learned, because I'm doing some of this stuff for work. But you can actually look at that SPKI, which is just a bunch of bytes, and you can do a SHA on that and get a and then base64 that, and get basically a representation of that certificate. And you can take that and save it, and assuming you were connecting to the right place in the beginning, there's always that, like, chicken before the egg. If the NSA wasn't already doing the man in the middle at that point, you can get back the actual real information about that certificate and pin it. And what that means is when you connect again after that TLS handshake, or during the TLS handshake, you can look at that certificate, calculate the pin, and say, is this the pin I had before? And if it's not, say, something's wrong. So Chrome actually does this, but it gets a little crazy, Twitter especially, but other CDNs. Twitter has, I'm not even joking, like 40 certificates for all their different servers. So when you go to twitter.com, in Asia, it's a different server versus Georgia versus Colorado, because they have a big CDN. And if you use other CDNs, like Amazon's, like CloudFront or Akamai or whatever, name your favorite CDN, when you go to that host name, it'll be a different thing, and they may not necessarily have the same certificate. Now, the way around this is having a pin set. So actually, Google Chrome, if you can actually look at the source code and see there's a couple JSON files. One of them is not JSON. One of them is a big list of certificates, and either the actual raw certificate information, like I showed you with the certificate and the dashes, or it's the actual pin. And those are all named. And then in the other file, in the actual JSON, they set up this crazy structure that says twitter.com maps to this set of pin names, or pin, And so it's like kind of a many-to-many thing. And you can also have Google actually shares a lot of their certificates. So mail.google.com, plus.google.com, www.google.com, all those use the same certificate. So those would always point to the same. Those would all point to the same pin, whereas twitter.com is crazy. That's a bunch. So it's a many-to-many kind of relationship. So it can be a little tricky, of course. This is one thing I'm doing for my project at work, and I'm like, this is kind of hard. But it's still pretty interesting, and this adds another layer of security. And I think as we get better at this, like Google Chrome will do it more. And the main thing is you can do it with your own services. So like if you have a really important API that you're connecting to over HTTPS, you can pretty easily do some pinning on that. I mean, this is basically the code for it. Given a certificate, You create a new SHA. It could be a SHA-1 or a SHA-256. You write the raw public key info, and then you base 64 it. Boom. And then a lot of the Google Chrome ones are, I think, all SHA-1. So if you want to match the ones, if you want to double check your work, you can find that list of the Chrome ones and do a SHA-1. You can actually compare them and see they're the same. So this is how you do pinning. Pretty quick. You can just have this in your app and check the pin on whatever your email API or wherever to verify that you're actually talking to the right person. So I guess to conclude, pretty quick, as a developer, you should take the time to learn about security. What I've learned, I am by no means a TLS expert. Like, I can't tell you the details of the key exchanges and how they work and elliptical curves, and I mean, I know some of the basics of it. But you can learn enough to really be a lot more educated to tell people when they're like, oh, the NSA can read everything. No, they can't. Tell them that, which is true. Or whatever, that like, we don't need to use HTTPS. You probably should. Because it serves a couple things. Another thing that I actually learned recently, and part of all this, you're also getting security, but you're also getting message authentication and verification, importantly. Like it's impossible to have a corrupted HTTPS message. Like, because of those CVCs and checks that it does. It's checking that the integrity of those bytes that have been sent over the network is correct. So you can make sure that, besides being secure and untampered, that it is correct and that like some byte wasn't lost in the internet somewhere. So knowing that makes you a better developer. Like I said, you can educate your family and friends and let them know that certain things they should do and not to worry about the crazy things like hackers will be able to break my encryption. They won't. And you should know enough to protect yourself as well. So Go, fortunately, I think can make security a bit easier to understand and implement because it's a pretty easy language. It's easy to read anytime you want. In case you don't know, I'll show you real quick. Actually, I may not have internet. Is there a?
There's a
There's a guess.
Multi guys.
I'll go to. That's funny. I'll trust theirs. Let me go to Safari. I already have something. So like, let's say we're in that. So like, here's like listener. I was doing some stuff with listener the other day. So if you actually want to look at the code, you just click it, and like it highlights that section, and you can just check out everything around it, errors, whatever. And TLS, you can actually like look at the handshake code, which I actually haven't yet. I was considering taking a look at it, see what it does, see if I can like explain it. But so get a mutex. I guess there's depending on which side you are, yada yada. Yeah, there's tons of code up here probably. Anyways, so yeah, you can look at I don't know. This to me is much easier to read than the C in OpenSSL. So I guess that's that. Thanks.
Any questions?
That I want to answer.
I have a question you might not have the answer to.
Yeah.
On Let's Encrypt, do you know if their root CA is trusted by the major browsers?
I think that is why it's probably taking so long for them to release.
Okay.
So yeah, they have to. Actually, let's check that because I'm going to assume they're using their own CA. Go to full screen. So as you may or may not know, you can just so yeah, this is the chain. All right, so I guess their certificate is from someone else, unless that's them. So yeah, probably at some point, you want to see like everything that's in a certificate. There you go. Subject, issuer, signature algorithm. There's the before and after validity. This is like, it's from February, I it for years. Kind of public key, about to say 248 bytes, that's good. Signature, yeah. So anyways, maybe you understand this a little bit better. I don't know. All this stuff is the things I like didn't show you in that X509 certificate.
You hit technology certificates based on how they're going to give browser support.
Oh yeah. Cool. I mean, it seems like it shouldn't be that hard because, you know, a lot of the modern browsers are open source. You know, I mean, it's like a pull request away. I mean, I guess you still got to verify it because if it's like, you know, hello, we're from Iran.
Yeah.
Can you add this root CA so we can spy on our citizens? That's the problem. I mean, and there's actually people working on things like, you know, a distributed trust model, and where you can not have to rely on these, you know, people that, I don't know, somebody decides they trust them. And there's some cool stuff going on. Actually, I should mention this as well. I'm just going to just surf the internet and show you cool things. MadeSafe is really cool. So they're basically, it was a C++ project that recently switched to the language Rust. And it's like really cool. It's basically, it builds another internet on top of the internet. It's kind of like BitTorrent, but more controllable. So like you can build apps on top of it. So this is kind of relevant because everything's encrypted. They basically, you say, I will allocate like 20 gigs on my server or my laptop for MadeSafe, okay. And then they give you some credit on their system for that. And then all your data that you save is basically split up like BitTorrent does and encrypted and like thrown all over the world with like 5 or 6 copies. It's pretty cool. So like, you know, if somebody's has a piece of your data and they shut off their laptop, that's no big deal because it's like in 3 different places. Pretty cool stuff. They're a startup. They got a good amount of money, so they'll go places. And these are the things you can do. You can be a developer, build an app, or be a farmer, which is this person that says, hey, I'll just give you a shit ton of servers, and you give me a bunch of, they have something called SafeCoin. It's kind of like Bitcoin. So anyways, yeah. Any other questions? All right. Well, we can talk.